My name is Chris. I work for Twitter. This is a very long presentation, but I just show you the second half of it because that's the interesting part. So I'm assuming everyone in the room knows what Bayesian optimization is. Very good. So I don't have to explain it. Yes, I'm going to skip a lot of slides here. So you guys know what Twitter is. We run on microservices, and we have a lot of them. And so this talk is about we're using Graal to run our mostly in Scala written services. And by using Graal, we save a lot of CPU. So what we also have is something called, I'm not sure if that will come up. Yeah, so we have something that's called Autotune. It's basically a framework that's using a Bayesian optimization as a machine learning framework to tune JVM parameters. And so we can pass in to Autotune, we say, oh, tune this parameter for me, and then Autotune talks to the Bayesian optimization part, which is wet lab. There's also an open source version of it called Spearmint, if anyone has ever heard of it. And so then Spearmint or wet lab figures out the next, you confused me. The next value of the parameter to try to explore the space and then find the optimal configuration. So it's a driver. Autotune is the driver to run these experiments. And people know what Graal is, so I skipped that. You can watch this on YouTube if you want. And so these are the parameters that I tuned. There's one called trivial inlining size, so that's the size. By default, it's 10. If a compiler graph of an inlinee is smaller than 10 nodes, it just inlines it without looking at any other data. Then there's a maximum inline size. That's the other end, basically. If it's bigger than 300, it doesn't inline it. And then there's something called small compiled low-level graph size. It's similar to the second one, but it's just a low-level graph, so don't worry too much about it, what it does. But these three parameters are the ones that affect inlining the most. All right. So I did some previous work. I have another talk where I explain how cool Graal is and how much CPU we're saving. And so these are two slides from my previous talk. Look at blue and orange, basically, so this one and down here. By just using Graal instead of C2, running our stuff, we can reduce parallel GC cycles by about 3.8, 4.2%. No, actually, no. Yes. Yeah, 4.2. And what I did when I ran this a year ago, I think, I manually tried to change the three parameters you just saw to figure out if we can get better performance out of it. And so what I was able to do by sitting down an afternoon and trying this for 2-3 hours, I could reduce it by 1.5%. And I did the same for CPU time. So basically, by just running Graal, we can reduce CPU utilization by 13%, which is a lot, and saves us a lot of money. And I could squeeze out another 2% by manually fiddling around with these. But you don't want to do this manually for every service. You want a machine learning framework to do this for you, right? So that's exactly what this is. So this is the configuration, but it's a JSON file that you pass into Autotune. It's basically the parameter, and then you tell it the range from where to where it should, explore the space. You don't really have to specify that. I've ran experiments after this where I just said 1 to 1,000, right? Because it doesn't matter. The framework will figure out what the right parameters are. I just used a range here because I wanted it to work for the talk. But I'll probably rerun the experiments and just set it to 1 to 1,000 and let it figure it out itself. So the test setup is I have dedicated machines. There's nothing else running on them because crosstalk is a big issue when I do this performance evaluations. All instances receive the exact same requests. That's important. It's not the same number of requests. It's the exact same request because a tweet could potentially be 1 character 280 long. And then that would affect memory allocation a lot, and it would change the outcome. We're running with this version of Graal, default tiered setup C1 and Graal, so there's nothing we change here. So the first experiment, is the tweet service. I have two experiments. I'm not sure if I can show you the second one too because of time. The tweet service is basically reading and writing tweets. It's built on Finagle. It's a framework, an open source framework that we developed, and you can get it on GitHub if you want. It's an extensible RPC system for the JVM used to construct high concurrency servers, blah, blah, blah. I have no idea what it is. But the most important part is it's 92% written in Scala. And Graal can handle Scala very well because Scala allocates a lot of temporary objects, and Graal's inlining and escape analysis are just better than what C2 has, and that's why we can reduce the memory allocation rate, reduce GC cycles, reduce CPU utilization, and so on. Okay, so you have to pass in an objective, right? In this case, it's use of CPU time. And since the AutoTune framework looks for a maxima, we invert this one to find, the configuration that uses the least CPU. And then you can specify some constraints. In this case, it's something, so we run on Aurora in Mesos, or the other, in Aurora on Mesos. And there's something called when you get throttled, basically because you're using too much CPU, then it kills you. And so that's basically our constraint. We say, because if you tune, sometimes and I noticed that when I was tuning it manually, that sometimes you specify some values where the service doesn't even come up because they're just too wild. And so we have to put in a constraint so that we know if we went too far. So this is 24 hours of doing an experiment. One is only 30 minutes long. It's called an evaluation. And I picked 30 minutes because it's long enough for the tweet service to actually reach a steady state. And I wanted to have a lot of evaluations so that we see how AutoTune really works. So as you can see, this is just requests per second, and it's the same for all of the services for the two instances. And this is user CPU time. So the experiment is blue, and the control, which doesn't change, is orange. And if the blue line is below the orange one, that means we see an improvement. And if it's above, then it's worse. I have the same graph slightly different here. It's a little easier to see. Every time when it's below, it's better. When it's above, it's worse. And the result, when this was done, looks like this. It's a web page. It shows you all the experiments. And then this one's the best one. And you see the objective is 1.0838. That means we could improve CPU utilization by over 8%. And these are the parameters. You remember, I said 10 to 25. This was by default 10. This was default 300, and this was default 300. So if you use these parameters, then you get 8% less CPU. And the bottom of the table looks like this. We have 3 ones that violated the constraint. We have 1 that's still in progress when I shut down the experiment. And as you can see, there are these that were worse, like this one's almost 5% worse and like 3% worse. Now, these are charts of the 3 parameters. I'm showing them. It's not perfect because it's a 3-dimensional space we're exploring, because we have 3 parameters, and it would be n-dimensional if you have whatever parameters. But it can give you a picture. Every point in here, every data point, all depends on 2 other parameters. So, keep that in mind. But if you squint a little bit, you can see that there's actually a trend going up. So if you increase trivial inlining size, you get a little faster if you do more. But at some point, it's too much, and it's coming back down. And this is maximum inlining size. It's kind of flat. And then this one, you don't really have to squint to see what's going on. So and that one's by default 300, so we would be in that area, and we can improve it by that much if we, increase that value. I didn't look at the time. How much time do I have left? With all the stuff in the beginning. Okay, so what I did then to verify the result was I took the parameters, the top one, and ran a 24-hour experiment. I also call it an experiment, but basically a verification experiment. I just ran the tweet service for 24 hours with C2 Graal, and then Graal with the AutoTune parameters in red. This is, again, PS scavenge cycles, because tweet service is using a parallel GC. And as you've seen earlier, in this particular run, it was 3.4% less GCs. And with the auto-tune parameters, we could increase that by 3.5. So in total, we can roughly reduce GC cycles by 7%. And the funny thing here is that that auto-tune actually squeezed more out of it than it did by default. And the same graph, it's basically the same graph as the one before. I'm just showing this one. It's allocated bytes per tweet, and it's very flat over 24 hours. And you see obviously the exact same improvement here, 3.5, 3.4, 7% roughly. And this is user CPU time. As you've seen in the beginning, that's about 12%-ish in that particular run. It varies a little bit. And with auto-tune, we can bring that down another 6.2%, which gets us to 18% less CPU. We have our own data centers. We own our own machines. But even in the cloud, if you can run your business with 18% less machines, it's a lot of money you don't have to spend. And also, you save electricity, you save on cooling, blah, 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 all that stuff. So we're actually trying to save the world here. Right. Then this is latency, P99 latency for tweets. And you can see it's certainly, Graal is certainly better. It's a little hard to tell how much it really is. Auto-tune looks like this. It's certainly better, but again, hard to tell how much it is. So what I did was I was integrating over the GC times of 24 hours, and that's the graph of that. And as you can see, we can reduce P99 latencies by 19% by just using Graal, and then another 8% by using the auto-tune parameters. So 28% means you get your tweet 28% faster. And you should tweet that. So I think I have 5 minutes left, so I'll skip this one. It's basically the same with a different service. Let's just go through this. So you've seen all that, blah, blah, blah. I would say the same thing. 7.6%. And yeah, these graphs, you've seen them before, look similar. The run, 1.6, 3.5, that's interesting. That just Graal reduces its GC cycles only by 1.6%, but then auto-tune gets another 3.5 out of it. So,
but did it find different parameters for another service?
Yes, it did. It did. Here. No, here. 23, 398, 646. I can't remember the ones before, but yeah, they were different. Scroll, scroll, scroll. We've seen this. GC cycles, CPU time. So that service is also built on top of Finagle, but it's certainly not as CPU sensitive. I'm not sure what to say, but we could only reduce CPU by 5.5, but just using Graal, compared to 12 for the tweet service. And with auto-tune, we could reduce that by 7.8%. And I think the reason why this is actually higher than just Graal is the same as the GC graph, because we can reduce GC cycles by more, and that automatically means that we don't have to allocate memory, we don't have to GC it, and that reduces CPU. Okay, 13% questions. Yes, there's one question that everyone has. Correct? Yeah. Of course I did. I couldn't come up here and not have done that. So I picked these three. They're very similar to the ones that Graal has. It's max inline level. Graal doesn't have that. It's the depth of inlining that C2 does. At 9, it stops. So if you call more than 9 methods, it's just not inlining anymore. Max inline size, 35. The same as the Graal parameter. Basically, the only difference is Graal is looking at nodes in the compiler graph, while this 35 is bytecode size. There's a funny story about this. If you have assert statements, that actually is counted in that 35, so it's stupid. We never fixed it, but JSON configuration, kind of the same, 5 to 20. I wanted to see if actually less inlining level changes things. Experiment, that's the outcome. Same graph, that's the result. So the best we could do is 5%. And that's kind of, I think, an outlier because we see here 3.8, 3.5, 3.3. I think that's more the range that if I would run the experiment, which I didn't do yet, the verification experiment, we would see a rough 3.5% improvement that AutoTune can get out of C2. Nice, right? So AutoTune does a very good job, but compared to Graal, it's just nothing. Because this is the tweet service, and we had, what, an 18% improvement by using Graal with AutoTune, and the most we can get here is roughly, let's say, because I'm nice, 4%. So. No, it's not. No, it's not. Because this is Scala. C2 is not tuned for Scala. That's an interesting chart, the max inline level. You can see it goes up. So 9 is the default, right? So we're around here. We can, certainly it should be probably 17, to be honest. And then this graph, flat, flat. So they don't change a lot. Yeah, that was it. My summary is always very simple, and I always just ask people, please try Graal. As you saw, especially when you run Scala code, you should certainly try Graal. It can reduce, the cost of your whatever you're doing, business. And I want people to try it so that we find more bugs and can make Graal a better compiler. So if you try it, run your pet project, or I don't know, you go to work at Monday and put it in production, that would be cool. We do it. So if you get a crash, that would be nice. File a bug. If something doesn't work as expected or is slower than C2, yeah, file a bug. If it's better, tweet about it and at me. I would love to hear it. So that was it. Thank you very much. Any questions? Yeah.
Use the microphone, please.
So did you run these experiments only for 24 hours?
Yes.
Or, okay, because if you look at the parameter space, it would be over 3, with the parameters you showed, there could be over, if I'm right, 3 million configurations?
Yeah, possibly.
Yeah,
but
so
the problem is you didn't see the first half of the presentation.
yeah, but I know what Bayesian optimization is.
Yeah,
So-
so if you know what it is, then you know how it works. So it's
Yeah, but
not,
it's also sometimes very fragile, so,
not really.
okay.
I mean, you saw.
Yeah, but there are a lot of other things out there, like how do you batch this? Can you batch it? Like there's a post by Facebook where they used the same technique for their hack compiler, I guess, was recently posted.
Okay.
And they show that there's quite some evaluations needed. So I was wondering, is it feasible for everyone, like besides Twitter, to, like if you have a production workload,
Right.
to try this?
Oh, absolutely. So I did 40 iterations,
Yeah,
right?
okay.
That's a very good size, I'd have to say. If you look at the table, the results table, you'll see that the top, it kind of, you explored the space enough so that you
Okay.
have a good result. The goal, we're not there yet, but the goal is to have this always on for every service so that the services are tuning themselves automatically all the time. And then you can run 30-day experiments or something, right? You don't have to tune it every day. The code is changing, yes. Everyone is deploying multiple times a week, but it's not that much, right? If you tune it once a month, it's still 100 times more than you would manually tune it, right? You only tune it manually when someone gets upset, and then he tunes it, and then, I had this at Twitter. I got there and I said, hey, when was the last time you tuned the parameters for the tweet service? I said 3 years ago, right? That's basically what happened. So we want this always on. And then we can run, 30-day experiments and run it a day for one evaluation or something.
One follow-up is
Sure.
there any intention to make this AutoTune framework open source?
Yes, there is.
Okay.
So the problem, the wet lab, Bayesian optimization part, that probably we can't open source because we bought that company and, complicated. Okay. But there's the Spearmint framework, which is open source, and then AutoTune, we wrote ourselves, our team, so yeah, we can open source it. It's just at this point, it's not very user-friendly.
Okay.
I have to curl JSON files to an URL, and then, you know, and you can only kill all the experiments. You cannot kill one of them. So it's, you know, it's work in progress. But yeah, we want to open source it. Microphone.
So there exist about 1,000 XX parameters. How many can you tune at once, and how do they interact with each other?
So how much time do you have? Right? You can tune all of them if you want. The auto-tune was written to tune GC parameters. That's why.
How many at a time? Like 3, or you can?
No, you can
4,
as many
5?
as you want.
Okay.
Yeah, it's like the space will be a little bit bigger, but yeah, you can do as many as you want. Wrapping up. Okay, that was it. Ask me later. Thank you.